are live and in the studio, well, it's actually the warehouse, with Dr. Tom Dykstra, and we're going to talk about electrical conductivity today. But before we do this, we want to reiterate, and I may sound like a broken record, and I hope I do, the penetrometer, please check that first. 100 to 150 psi allows air in and out of the soil. If the soil can't breathe, if you can't breathe, nothing else matters more than a breath of air. So make sure the soil can breathe. Number two, we want to take a look at a heartbeat. This is the EC meter, the electrical conductivity meter that measures the heartbeat of the soil. And the third thing that we will talk about later is the blood panel, or the plant sap, or the fluid that runs through the veins of the plant that can be analyzed to see how healthy or how sick it is. But today, right now, we've got Dr. Tom Dykstra, a quite famous entomologist and scientist from Florida, that's going to speak a little bit more on the EC meter. And before I turn it over to you, what we find is most plants, and I'm curious to see what you have found, but most plants on this EC meter, the initial growth of the plant needs a 0.3 to a 0.5 or 0.6. That's root, stem, and leaf. Once that plant goes into flowering, silking, tasseling, blossoming, we find out that reproduction needs energy. And what was a 0.3 to a 0.5 in the beginning now has to be a 0.6 to a 0.9. But if you get over a 1.0, things start going backwards. You had told me and showed me very many years ago that soil microbes actually have electricity in their body.
They do. Not only is it the electricity that we're referring to, though, but it's also the stored energy. And that is, in order to make a cell membrane, in order to make a chloroplast, in order to make the Golgi apparatus, in order to make the nuclear membrane, all the cell parts need energy in order to put them together. Once they are put together, they are what we call stable. And the cell is stable and is able to swim around and do whatever it does in its life. But because it took a lot of energy to put it together, that is a type of stored energy, much like a battery. And so therefore this energy, which is inside the cell, has been approximately measured. In other words, how much energy did it take to put a single cell together? Now the single cell that was analyzed in detail is E. coli, which is one of the smaller bacteriums that is out there. So it's a very small cell, and just in that small cell, the amount of energy in it was about a half a volt. Not a half a millivolt, which maybe is what sometimes people think. We're talking about a half a volt, therefore 0.5 volts. That's the total energy that is found in a given cell. Because that's a significant amount of energy, because obviously if you do the math, you would say, oh, I only need 18 cells in order to make a 9-volt battery. Yes and no. Obviously, if you could take that energy and completely pull it out and store it in a battery, yes, that would be an equivalent. But that doesn't mean that electrons flow the same way as a battery does, because it's actually set up in order to have energy flow in a particular way. A cell doesn't have that much energy flowing in it. Most of it is in a stored form. However, having said that, there is a significant amount of energy that needs to be flowing. We need to have energy flowing through our body. Many people are aware of the nerve cells in our body. We're also aware that if we are touched, so if I have a sharp point and I touch the tip of my finger like that, that may, if I pushed it hard enough, might send a message to my brain that I've just been pricked by something sharp, and that I might even be able to draw blood, and therefore there might be some pain that is coming from that. We know that the nerve message transmitted from the tip of my finger goes to the brain, and it's a unidirectional type of thing. What people are not aware of is that there is also an alternative energy flow, and those are the Schwann cells, the blanket cells that surround the nerve. So the nerve is going to be having a unidirectional flow, mostly going to the brain, while most of the electrical flow going on the Schwann cells is exactly the opposite. And this I wouldn't call it equal and opposite, but this opposite charge of the cell is important for life. And so we've got energy going in one direction, we have energy going in another direction, and the success and our ability to function as human beings, and by extension, microbes, insects, and plants, is about how well this energy flows in our systems. If we put a blockage there, it doesn't flow. And so that's why we want to make sure that things flow well. We have, in this warehouse, we have a number of electrical outlets. They all have copper wires, which are bringing energy to that. I want to differentiate between energy and electrical conductivity. The energy is something that we usually measure in volts per meter. It's a very common form of measurement, but I'm not talking about pure energy in volts per meter. I'm simply talking about the flow of this same energy. And the flow of this same energy is going to have a different unit associated with. This is where we get the microsiemens, among other things.
Does this pick up microbial energy?
If you kill it, yes. So if you stab the microbes and you kill it, the contents of it will flow out and you will be able to detect that energy because you've now essentially punctured a battery. And as it's oozing out, there are going to be certain salts, healthy salts, that are associated with it.
Organic salt?
Organic salts.
Not inorganic.
Not inorganic. Those are going to be totally different, usually unhealthy type of salts. And so these organic salts, yes, can be directly measured by this. We have found, I'm talking about others who have done the research, have found that organic salts can reach a high of 1200 or 1.2. Depending upon the scales. There are two different scales that are often used in electrical conductivity. So I just want to mention both right now to you, that whether or not you're dealing with 1.2 or whether you're dealing with 1200, this is just a movement of the decimal point and has to deal with the units, which sometimes get interchanged back and forth. My preference is to use, because I would prefer not to use the points if I can. So when we're talking about 0.2 or 0.3, I prefer to call it 200 and 300, simply because it's just a change of units. That's all that it is. So if you go to the literature, you will find both, just to let you know. So this one, I believe, is the 0.2, 0.3, 0.4. There are other instruments that will give you in the hundreds, so you don't have to deal with the points. But know that they're synonymous.
Can I jump in for a second?
You may. Thank you for asking permission, by the way.
Years and years ago, I was trained with the whole numbers, which measured ergs, E-R-G-S, energy released per gram per second. And what they found out is if you move the decimal point 3 places, you'll get microsiemen. Correct?
Microsiemen, millisiemen.
Or millisiemen.
Both of them are used. So
yeah.
Because whether you're dealing with microsiemen or millisiemen, that's the decimal point change.
Millimos, millisiemen.
That you're referring to, yes.
Yeah.
That's all that it is. So
yeah.
So
and a lot of times when you look at the change between a 0.2 and a 0.3 on this meter, it's like it's a tenth of a point.
I know, it doesn't seem that much when you're on that scale.
And a 0.2 to a 0.3, going back to the old ergs, would be between 200 and 300, yes. And all of a sudden now it's like, whoa, that's respectable.
And it sounds more respectable in our minds.
So it's all about perception.
Yes.
But with this, what we have found, and I'm guessing you're doing the same thing, is there's readers on each of the metal tips. And if you stick it just in the soil to see what your number is, if that number is high, a lot of times it's sodium. And as you push down very slowly, watch this number and feel the pressure that it takes. Because many times if the pressure gets higher, you've gone into anaerobic soil, and many times this number will bounce up because there isn't any oxygen in that soil to pull the nutrients out. But getting back to this, as you push this down, the more consistent the number is, the more biologically homogenized that soil is. My question to you is, how long do some of these soil microbes last? Because you said if we kill them, we can check the energy and burst them.
Yeah, because anytime we thrust that into the soil, you're probably going to be killing, dozens, hundreds, or thousands of microbes. And that's partly how we get the reading that is there. So I do want to differ with you on one point. I mean, I like you and everything, but I'm just going to have issue with,
Of course,
with one thing, and that is they have found when you place sugar onto a soil and therefore increase the microbial activity, you can actually increase the electrical conductivity of the soil. And so therefore, it's not necessarily, I didn't want to give our viewers the idea, and I'm not sure if you meant that, but it may have been perceived that way, is that once you go from aerobic down to anaerobic, there's going to be that jump. Therefore, the perception being is that the aerobic bacteria don't have as much conductivity as the anaerobic, which is not true. So if you increase the aerobic activity by simply adding sugar and therefore increasing the microbial population, the electrical conductivity will increase as a result of that. So that's, I just wanted to mention. I just wanted to make sure in case anybody out there takes offense at that and then decides to write us a nasty letter.
well, your honest opinions are always welcome. Question. Why, when you say sugar,
Yes.
white household table sugar?
That'll work.
Why would you put sugar on the ground?
You would put sugar on the ground in order to increase the microbial activity in the soil.
Which would increase the conductivity.
It does.
Which increases the movement of nutrients.
Yes.
Which feeds the system.
Yes.
To grow food.
Correct.
Aha!
He is following along. He can be taught.
I'm slow, but I'm consistent.
Yes. And so because of that, we've got this, it's not necessarily a measure of life, but it is an indirect measure of life because we can see as things improve, like in the soil, and therefore it's going to be reflected on the plant, that there's going to be an increase of health associated with that. And that increase of health on the plant would be measured in Brix, B-R-I-X, as opposed to B-R-I-C-K-S, which we use in order to construct various walls of those sorts. So because of this, we're now dealing with a different phenomena than what we may be used to. And this is, it's actually important though, because there's actually a beautiful progression or chart which can be done in order to see how well plants do. Now, what Glen had mentioned earlier on, and we found almost identical numbers associated with them, is that when it is at 200 and below, we have very low microbial activity, but you're also going to have poor, low Brix plants. These are going to be stunted growth. The stunted growth plants will not be performing up to par because there's not enough flow of electricity. And so because of that, when you are between 0 and 200, and we can get very close to 0, by the way, in sandy soil.
Oh, hang on.
Yes.
0 to 200 or
0 to 0.2.
Okay.
Yeah.
Interchangeable terms meaning the same.
They're really interchangeable,
okay.
Yes. So
okay.
it's good to kind of repeat this, especially if someone's coming later on in the video and didn't see the beginning of the video. They're going to be.
They may have been grabbing some popcorn.
They might have grabbed some popcorn. That's good stuff.
So the low number would be a low battery or low microbial activity.
They're related to one another, yes. They are related to one another. Once we are between 2 to 600 or 0.2 to 0.6, this is what we call a very comfortable zone. It's an organic zone, and it's used often in many plants. It doesn't matter what the plant is. It doesn't matter whether it's an early growing tree, a bush, a crop plant. They're looking to be in the vegetative state at around 200 to 600. Those are the readings that you will get. And the reason why, and it's relatively low, not too high yet, because they need electricity flowing in order to make things. Now, making things like roots, stems, and leaves is not hard. It is like, and I'm going to use this analogy on purpose, it's like bricks. When you're B-R-I-C-K-S, when you are putting bricks together in order to make a wall, this wall can add a massive amount of structure to a building. It is very obvious that a wall is going up. We see it just as we see the plant growing, and it's not hard for the plant in order to make that wall. What does become hard is when you move in the other subcontractors, when you have to move in electrical wiring, when you've got to move in plumbing, when you've got to put on roof trusses, when you have to put on hurricane strips, when you've got to put on shingles, when you've got to put on the rest of, let's say, a house, it becomes much more complicated. When you move to that next complicated stage, and now I'm referring to a reproductive stage, you have to ramp things up. You have to amp things up. Both of the words, actually.
Oh, play out.
Notice how I played it.
Shocking.
It's so...
Moving on.
Moving on. We shall move on. So therefore, once you move to the reproductive phase, there are a larger number of proteins that are being used in order to make the sepal, the petal, the pistil, the seed, the fruit. All of these reproductive structures are much more complicated than simply making roots, stems, and leaves, which essentially is a lot of repeating units, such as the brick analogy that I made, B-R-I-C-K. So once you move on to a complexity, not only do you have more proteins that are being made, which adds to the complexity, but you've got a lot of enzymes which have to be added to the mix in order to make sure that everything goes together exactly where it should be. Because of this added intensity and the added complexity, this is the reason why electrical conductivity or the flow of energy needs to go up. And it should. And if you leave the plant alone, it will do it on its own. It will start to release more sugar from the photosynthate that it's producing in the leaves. It will remove more of it from the leaves, send it into the roots. It's going to start to pick things up. It's going to have more nutrients going in. And this whole process, the reproductive process, is going to be very optimal, at least we have found, between about 0.4 and 1, or 400 and 1,000. So there is a little bit of overlap there, and I think you kind of see that there. But the overlap, though, is that you can have a plant at, let's say, 500 or 0.5, and it'll go through the vegetative stage very well. And if it stays in the reproductive phase through that 0.5, it will suffer a little bit, but it'll still make it. It'll still go through and it will make the fruit that it needs to do. But it won't be doing so at the level that you, the farmer, might want it to be. You want it to go up. If the plant is able to go up, it will. So if it chooses to go up, it will ramp things up, and then it will make it happen. And you will notice it with the electrical conductivity in the soil, especially around the plant. Once you get to 1,000, some plants, not all, some plants start to suffer. The most obvious one, according to the literature, is green beans. Green beans are the most susceptible for reasons that are not completely known, but I'm sure there are some who are aware. But the green beans suffer a fair amount when you get to about 1,000 or 1.0 on the scale. And that's because the electrical conductivity is a little too high. Things get a little too hot for green beans. So because of that, the yields will start to drop. On the other hand, having said that, in the laboratory, good organic salts can be tested, and they will max out at about 1,200 or 1.2. So knowing that is that you really can't reach anything above 1,200 unless it's inorganic, is that up to 1,200 you can raise most plants quite well.
Wait a minute. You lost me.
I did.
Organic salts, inorganic salts.
Yes.
Help me out. Tell me if I'm right.
Okay.
Microbes can take a metal-based mineral and a non-metal-based mineral, and there's about 1,000 combinations, and they can digest and create an organic salt.
Mm-hmm.
These organic salts don't burn, they don't kill, they don't destroy. They are created by the microbes, for the plant, for the ecosystem.
He is much smarter than he looks. Wow, that was good. Keep going.
Doesn't say much. What an inorganic salt is table salt. And I think, I have nothing to back me up, but I've got a sneaky feeling that the synthetic fertilizer companies started putting inorganic salt, table salt, sodium chloride, into the fertilizers as they saw the microbial activity slowing down and dying. Agree, disagree, or...
You are correct. Once again, Mr. Rabenberg, congratulations.
So is that why there's salt?
This is a huge part of why there is too much salt in our agricultural lands. But please understand why they do that. This is not about necessarily pure evil. They do this because they don't want it to explode. Fertilizer plants do have the nasty reputation of sometimes exploding. And so in order to stabilize these fertilizers, they are then mixed with a salt. And therefore, it's usually sodium. Sodium is usually attached to the fertilizer, which stabilizes it and gives it the ability not to explode in your face. Well, it's not just the fertilizers that do that. It's also the pesticides. The pesticides also have a certain danger associated with their usage if you're handling them a lot. They are also stabilized with various salts. And it's usually, not always, but it's usually sodium, which is done in order to stabilize the insecticides, herbicides, fungicides, nematicides. All of these things are usually stabilized with salt. Therefore, when you are putting nitrogenous fertilizers in the soil and insecticides.
Nitrogenous.
Nitrogenous. Oh, did I use a big word?
You lost me. Nitrogen-based?
Nitrogen-based.
I'm not a doctor.
I get it.
Thank you for reversing.
I'm going to come down to your level and speak to that.
It's going to hurt.
I know.
Welcome home.
Thanks.
So a nitrogen-based fertilizer.
A classic NPK type fertilizer is what I'm referring to. So if you go to the store, and they'll usually have an NPK, and they'll have 3 numbers associated with the particular fertilizer that you may be purchasing. And that's usually a sign that we're dealing with a classic salt-based NPK fertilizer. So that's what I was referring to.
We see a lot of farms across the U.S., other continents, especially Australia, that have high ECs, and they have high salt, high sodium, and the electricity is getting so bad. And what we found is when you get to 1.0, these soil microbes, in my mind, I believe, are union. And they say, 1.0? Oh, no, it's way too much electricity. We're not going to work. We're not doing anything. So as we look at all these different numbers, what is the downfall? We understand low electricity, it's a dead battery.
Mm-hmm.
Too much electricity,
also bad.
A stroke,
sure,
a heart attack,
yeah.
Disease, insects, weeds, pestilence, biblical proportions. Point being is, getting air into the soil is important, but also making sure the heartbeat is right, consistent, and steady. If the heartbeat is low number, what would be the first thing you would tell a grower that he needs to do?
He needs to get some table salt and put it out on his field.
No.
Do I have to
if we don't delete that, I'm going to slap him after the video. Epsom salt.
He may slap me during the video. I just want to make that clear right now. I don't think he's going to wait until this thing is over.
What would low battery?
Low battery.
So if you have a low battery in your vehicle,
yes.
If it's an old battery, you're going to pull it off and check the fluid.
Mm-hmm.
Maybe put a charge on it.
Yes.
How do we put a charge on the soil?
We put a charge on the soil by adding sugar. That's what I do. Because usually when you're dealing with a low battery, you are not dealing with enough microbes in the soil. And the microbes add a certain amount of healthy salt to the soil. And therefore, this is the type of salt that needs to be done in order for a plant to grow well. If we do not have the microbes in the soil, we just have pure sandy soil, then we're not going to get a fair amount of growth. Immediately, some of our viewers right now are saying, oh, he just mentioned sandy soil. I know a lot of plants that grow in sandy soil. But they are actually increasing the electrical conductivity right along the roots and no further. You cannot detect electrical conductivity in a very sandy soil a short distance from the root. Let's just say, a few millimeters. But when you are within 1 to 2 millimeters of the root, the electrical conductivity will go up far above anything that you're going to find in the sand around that. And so we have found is that if you are playing games looking you might have very low electrical conductivity. It could be below 0.1 in sandy soil, and oftentimes is. But as you are probing around, eventually it will shoot up to 400, 500, 600. That means you hit a root. That's what that means. Because the roots have the ability to control the electrical conductivity. They would like the electrical conductivity, the flow, to be within the entire structure of the root, the root mass, the rhizosphere. But they have difficulty doing that. And so because they have difficulty doing that, sometimes they have to choose that they can only regulate the soil directly surrounding the particular root or the root hairs, and that's all they can control. So we can find that it's not that, because sometimes I know people think, well, like, well, if I get below 200, nothing should be growing, and yet we see a lot of things growing. But in fact, they don't. They really do not when it gets that low. So if the roots cannot maintain it above 200 or 0.2, then there will be various stunting growth associated with the plant. So that's a serious problem, and that's something that the plant needs to regulate. And if the plant cannot regulate it, necessarily because it's a low Brix plant, it will die. And we don't notice those plants in nature because they're dead. And we only notice the plants that are doing well. They seem to be okay. And we know that these plants that are in nature that haven't been touched by man in any way are running between 8 to 18 Brix. They're doing pretty well for themselves. And because of that, the electrical conductivity is just one component where we will find that the electrical conductivity in these plants is also not high, not a high Brix, but within a comfortable region. And a comfortable region is going to be between 0.2 and 1.2. Things get a little uncomfortable as it gets closer to 0.2. Things get a little more uncomfortable as it gets closer to 1.2. I just mentioned the green beans having a little bit of a problem, more so than other plants when it gets to that point. But most plants are okay when they're at 1.1 or 1.2. Once you break that, I know that someone has sprayed nitrogenous fertilizers, there I use that word again, or pesticides down in order to get it above 1.2 or 1200. I know that because we can't do that naturally. And so once we get to that point where things are unnatural, some plants don't grow well. Of course, green beans are pretty much out of the picture. By the time you get to 1200 or 1300, they're not doing well at all. No one really grows them, but other plants can come into the picture. And I've got I've got a chart right now. The chart will show the full gamut of not only where the electrical conductivity should be for all plants, but I've also got various plants listed in order as to how high their electrical conductivity can handle before they actually run into trouble. Trouble meaning they die, or they stop yielding, or yields and reduction yields are evident at this point. And so all of this is related to the electrical conductivity. And so right now we have done our best in order to mess up this electrical conductivity in the soil.
We as in you?
We as in mankind. Yeah.
On a different note, when you're in the sand in Florida and we're doing a row crop or an annual crop in a heavier soil, a heavier clay,
Yeah.
I will have growers take this and I say, go into the rhizosphere where the root ball, the root zone is. These are heavier clay soils, and just push it down, watch your numbers. And then move out a ½ inch away from the plant.
Yes.
Push it down, look at the numbers. What this will tell you is, in a perfect world, the rhizosphere, the root zone, should be the perfect zone.
Uniform too. Yeah.
Yes.
Yeah.
Consistent, stable, accurate, healthy, bulletproof, so to speak. In most cases, in the rhizosphere, let's just say my fingers are roots, they'll check it, it's low, they'll check it, it's low, they'll check it, it's low, they'll just get past the root tip, and they'll check it, and it's higher.
Mm-hmm.
The root hasn't had a chance to get to that yet, and it hasn't drained the tank, so to speak, or the pantry of nutrients in the soil. And so with these low numbers, the microbes aren't able to keep up with the appetite of the plant.
Yes.
So the consistency of this number, not just during the growing season, but you don't get winter down in Florida, but in South Dakota we get winter. And what we'll see is when the crop is growing, if the crop is healthy, we'll have a 0.8, a 0.9. we harvest the crop, the sun starts going into the southern hemisphere, we start getting cool, our days start getting shorter, this number slowly starts going down. And it should, because as the soil temperature cools, as our sunlight is lowered, the soil and the microbes are going into what I call hibernation, going into sleep.
That's a fair word.
And many times we'll see a 0.02, a 0.05, maybe a 0.1.
Yeah.
But you want that soil to relax, because when it relaxes, things can now get restructured, so to speak. The microbes can still work. In our soil, the soil will freeze, and in the spring, it'll start off at that 0.02, 0.05, and it'll slowly start coming up. And if you watch the temperature as well as the EC, they go hand in hand. The quicker the soil temperature can increase in the spring, it's kind of like waking up. Some mornings we wake up and it's just like, oh, how about another half hour of sleep?
That's most of them.
Or some mornings it's like, wow, do I feel fantastic.
I haven't had those yet. But looking forward to it.
We're getting old, pal. We're not going to get many.
Yes.
The quicker your soil wakes up, warms up, the quicker it's ready to start growing something. In the fall of the year, the longer you can hold the EC and the longer you can hold the soil temperature will tell you that you have carbon that's in the soil and oxygen that's in the soil that isn't necessarily coming from a root exudate, because the crop has already been harvested.
Yeah.
So the EC meter, or the heart meter, can tell you a lot of different things about numbers that may not have ever been thought of, been important. And the reason we bring this up is because this is one of the 3 tools that we use, and I think you'll agree with this. If someone can tell us what the EC is, their penetrometer readings, and the bricks, we can normally tell them what the problem is.
I got a pretty good idea at that point.
Yeah.
Yes.
How to fix it. And here's the point being is, we're not against synthetic fertilizer companies, we're not against synthetic chemical companies, but we are for the farmer. We are for the grower. We want you to be healthy. We want you to be economically successful. And we want you to have a little time off to enjoy your family, your friends, or whatever it may be. So, is there anything else we need to add on the EC talk, Tom?
Do you want to go into dead zones or no?
Let's save that for another time.
Another time. I would be happy to.
Now, when you say dead zone, short definition of dead zone.
Everything in the zone is dead.
Okay.
Did I go too fast for you?
Obviously,
I think I went too fast for you.
So I think what he means is something where nothing is living.
Oh, yeah, that's another way of putting it.
Or economically feasible.
Yeah.
We will touch on that in a different video.
Let's do that.
If you want to learn more information about the EC meter on an extended version with what's his face over here, Doctor, they can contact or look you up at.
They can contact me at dykstralabs.com or
you don't have to be whiny about it.
Yeah, if you need more information, you can get on YouTube and do Thomas Dykstra search, and some of my videos will come up, and then you'll get some more information. Thanks a lot, Glenn. It'll be fine.
Never for a whiner. I'm Glenn with Soil Works with Dr. Dykstra. We appreciate your time. We hope this information has been valuable, and we look forward to seeing you at the next video. Thank you.
Thank you.